Hi everyone, my name is Sophie Chu. I work in the Carbon Group with Adrian Sutton at NOAA PMEL. We have the benefit of collaborating on technology development with the PMEL engineering group led by Chris Meinig. In this presentation, I'm going to give you a brief overview of the work we've done in the last 5 years to evaluate existing and emerging sensors to measure ocean acidification. The activity area that this work pertains to is research to understand vulnerability, and it primarily relates to theme 1 of the OAP research plan from 2010, which is to develop an ocean acidification monitoring network. The subtask that this work focuses on is to test and develop sensor technology to quantify and track ocean acidification. In further expanding the ocean acidification monitoring network, we first need to decide how well we want to measure OA. There are 2 levels of measurement quality established by the Global Ocean Acidification Observing Network: a weather quality level, which is sufficient to identify relative spatial patterns and short-term variation, and a climate quality level, which is sufficient to detect long-term anthropogenically driven changes in hydrographic conditions and carbon chemistry over multi-decadal timescales, i.e., an ocean acidification signal. Our goal in this research is to determine the best combination of sensors to achieve the highest quality data to track OA at fixed mooring sites throughout the NOAA Ocean Acidification Observing Network, or NOAA. Many of these sites are remote and can only be visited annually. This requires the sensor to be accurate, robust, easy to deploy and maintain, and able to provide high-frequency measurements for a year or more. The sensor has to have low power and reagent usage, as well as effective anti-biofouling measures. Now that I've described how well we would like to measure OA, let's dig into what tools we have to do so. First, let's look at how accurately we can measure OA in the surface ocean. In NOAA, there are 21 surface moorings in U.S. coral, coastal, and open ocean ecosystems that contain a standardized suite of sensors to measure temperature, salinity, oxygen, pH, and PCO2, among other parameters. The main workhorse of this network is the Moored Autonomous PCO2 System, or MAPCO2, or called Ceology by the commercial manufacturer, which can achieve climate quality data, take 3 hourly measurements for over a year, and has a 90% data return. Accompanying the MAPCO2 is the SAMI pH that can measure pH at weather quality and has a data return of about 65% in our network. Measurements are taken at about half a meter's depth that allow us to estimate CO2 uptake and OA rates in the surface ocean. However, many coastal processes that affect OA are manifested in subsurface waters, and many organisms that are most sensitive to OA are benthic and respond to subsurface water chemistry. Therefore, most of our most recent work has focused on what technology to use to capture OA in the subsurface. We used sites in Hawaii, Florida, and the Washington Continental Shelf as subsurface sensor evaluation test beds, based on being able to leverage monitoring activities that already occur nearby. So how well can we measure OA in the subsurface? The answer is not very well. This table from a paper published in 2015 that still holds true today shows a handful of commercially available sensors for PCO2 and pH that can, at best, collect water quality data. Sensors inside the boxes are for subsurface measurements. I want to make a note here that no autonomous sensors can be deployed on buoys that exist for total alkalinity, shown here as TA and dissolved inorganic carbon, or DIC, for surface or subsurface. However, there are commercially available sensors in the prototype stage that have shown promise at our testbed sites for subsurface sensor evaluation that I will describe shortly. But first, I want to describe our coral reef testbed site in Hawaii, where we conducted an intercomparison of 2 commercially available pH sensors, a spectrophotometric SAMI from Sunburst Sensors, and an ISFET-based CFET from Seabird. The 2 sensors agreed closely in the first 2 months of deployment, but after one of the CFET electrodes drifted, there was a clear deviation. We primarily use SAMI pHs in our network because we lack the ability to collect enough validation samples to correct this kind of sensor offset and drift, especially at our remote sites that we only visit once a year. At our other coral sensor testbed, we deployed a prototype alkalinity sensor by Sunburst Sensors called SAMI Alk. Preliminary results show some interesting dynamics, and we intend to continue these deployments at both coral testbeds to determine the sensor accuracy and whether we'll be able to integrate TA sensors into our network. We're especially interested in using TA sensors in coral reef testbeds because coral calcification influences TA, and therefore TA cannot be accurately predicted by salinity or two other parameters of the carbon system, as it can be in many other ocean regions, and thus requires direct measurement. Indeed, in the bottom figure, we can see that the salinity-alkalinity relationship is not strongly correlated, whereas regions where alkalinity can be predicted from salinity often see R-squared correlations greater than 0.9. Now we are going to move to our other test bed on the Washington continental shelf, a region that experiences high water column variability and summertime upwelling of corrosive waters. Here we tested a new moored profiling platform called the Profiling Prawler, or Prawler, containing a CTD oxygen optode and a prototype optical PCO2 sensor produced by Indera. This low-power package was deployed for 2 months in the Northern California current system. PMEL engineers developed a mode to enable parking the Prawler at specific depths to allow for optode equilibration. We tested this compared to the free-falling mode used at the beginning of September. Raw measurements of temperature, salinity, and oxygen are shown in the horizontal lines at depths spaced approximately 10 meters apart, and to its right are the contoured data. On the far right is the contoured PCO2 data from the optode with the different equilibration times that we used. This deployment was able to capture a low oxygen, high CO2 event in the mid to late December due to the evacuation of hypoxic waters from the south, confirmed by other moorings that we have in the region. In this application, the PCO2 optode achieved an accuracy at best of 35 microatmospheres, not meeting weather quality goals. However, we were able to use temperature, salinity, and oxygen data from the Prawler in combination with regional algorithms to calculate aragonite saturation state at an uncertainty of 0.15, which is within weather quality goals, and less than half the uncertainty of that using the PCO2 optode to calculate aragonite saturation. Corrosive conditions where saturation state was less than 1 were present for the whole deployment below 60 meters and up to 20 meters at the end of the deployment. The extremely low oxygen event in mid to late December corresponded with aragonite saturation close to 0 at bottom depths. Overall, this evaluation was able to establish the Prawler with a CTD and oxygen optode to constrain the water column variability of ocean acidification conditions in coastal regions similar to the Northern California current system, where algorithms have been developed to predict the carbonate system. Our key takeaways from this research are that there are few high-quality commercially available sensors to measure OA, though there are a couple of sensors in development, such as the SAMI-ALK, that show promise for making subsurface weather quality measurements for alkalinity. We also found that temperature, salinity, and oxygen combined with a regional algorithm can predict aragonite saturation state at a weather quality level. With that said, looking forward, there is a strong need to continue development of autonomous sensors that can make climate quality measurements, especially for the subsurface, and ideally ones that can be deployed for several months to a year. We are working to expand our climate quality measurements in the surface by developing the next generation MapCO2 system that will measure both PCO2 and DIC. In regions where carbonate chemistry can be constrained by temperature, salinity, and oxygen, we have a low-cost solution for high-frequency water column measurements that we can start to implement, but we need to continue to evaluate other subsurface OA technology that is still in development. And lastly, while there are several funding opportunities for early stage sensor development, there needs to be more funding for later stages of development in order to transition technology into commercially available sensors. This is likely one of the reasons contributing to the lack of commercially available OA sensors. Thank you.